Well, let's continue with our topical overview of the Seismic AVO playlist. We are looking at the remaining 13 videos here. And in the initial review, we left off with a discussion of the AVO gradient intercept approach, the Aki-Richards formulation of amplitude variation with offset, and we'll pick up here and just kind of briefly, as before, just kind of note the topics that we've talked about. We take a look at the lambda-rho, mu-rho formulation. This is one of the goals of the AVO work that we're heading towards, and that is to extract the lambda parameters, lambda and mu, specifically the products lambda-rho and mu-rho. And we're doing this because the lambda-rho, mu-rho plot that you see here, we're looking now at unconventional shale resources, specifically in this case the Marcellus, that lower lambda-rho and mu-rho values tend to be a good way to differentiate the high TOC regions within the producing Marcellus and other shale unconventional resources. So that's sort of a motivation for us, is to extract these values so that we can come up with information that will help us target the TOC-rich zones within the unconventionals that we're looking at and interested in exploring further. Now here we compare the gradient intercept approach, all three terms. We've got the intercept, the gradient, B, and then the curvature term here. So we're plotting them out separately in this amplitude versus offset plot. So the curvature term, we see that really not too much happens until we get out to the longer offsets. With the gradient, we see, in both cases, for a class 2 anomaly, a class 3 anomaly in this case, that the reflection coefficient basically becomes increasingly negative with offset. And again, we point out that when we stack these traces, the AVO offset is going to give you a response which is going to be significantly different than what you would predict just using the information from sonic logs and density logs. In this case, we might get a 0 reflection coefficient, no reflection coefficient. But an important point to emphasize again is that when we stack these traces together, we're going to see a negative reflection coefficient somewhere in this intermediate range, depending upon the range of offsets that we have in our stack. The intercept, again, is just a constant value. That corresponds to the 0 offset reflection coefficient. Now over here, this form is the form which is going to be of greatest importance to us when we start looking at lambda-rho and mu-rho, trying to extract the lambda parameters. And in this form, remember we mentioned that Russell in general will define the difference between two values over their average or over their sum as a reflection, kind of a generalized reflection coefficient. In this relationship here, after Fatti et al., these are actual compressional wave reflection coefficient, shear wave reflection coefficient, and then in this case we're looking at more or less an equivalent density reflection coefficient, if you will, just the difference in the densities over the sum. And we can see these three terms plotted separately, and then this would be the total. So when they're all summed together, we get this class 3 anomaly in this particular case. So with a 0 offset reflection coefficient that is negative, but when we stack them together, again, it's going to be, we'll see a higher negative value. But when we open up the gather and hopefully a common reflection point gather and go through the analysis, we are able to calculate what these coefficients are And the problem then is to estimate what the reflection, the compressional wave, shear wave, and the density reflection coefficients are. And once we do that, we'll be able to calculate the lambda-rho and mu-rho values. Again, that's a goal for us. So here with the taking a look at the kind of breaking the Fatti relationship apart, R sub p, we could express that as 1/2 delta Vp over Vp plus delta rho over rho. We go through the algebra here. We see that what we actually have is a reflection coefficient expressed in terms of the impedances. So, and this would be a shear wave reflection coefficient. This would be a compression wave reflection coefficient. And then down here we just have the density reflection coefficient. Now when we look at this equation, we should emphasize that the times we're going down through the gather from 0 to, or from whenever our data begins, down to some maximum time. And so we're opening up, we're looking at the gathers, we're looking at how the amplitude, how the reflection coefficient varies as a function of angle. And again, we have these three terms, each of which will come up with a unique value for the compressional wave, shear wave, and density reflection coefficients at a particular time t sub I. And so this is the kind of analysis that we would be undertaking with the goal of being able to determine in this particular thread, along this particular thread, to determine the lambda-rho mu-rho formulation, the values of lambda-rho and mu-rho. We see down here, but let's back up first. This comes from Goodway et al., and he reformulated the AVO relationships to help discriminate between fluid and lithology, specifically using the Lamé parameters lambda and mu. So he rewrote RF theta in terms of the Lamé parameters in this form down here. And so we can take this form and rearrange it, but first note that rho v sub p square is an impedance squared. Product of the density times the velocity gives us an impedance, and we've squared it here. And the square of the compressional wave impedance is equal to lambda plus 2 mu times the density. And the square of the shear wave impedance, we can represent by a capital I in this case, could be a z, is equal to mu-rho. So and then we can rewrite the above in this form so that we have R sub p, and again I'm emphasizing here that you're looking at reflection coefficient at each instant in time, t sub I, and then we have this ratio delta I sub p over 2 I sub p, delta I sub s over 2 I sub s, delta rho over rho, and these I sub p's, I sub s's, and so on, we can also think of them. We've been using both notations here. I sub p or z sub p, I sub s or z sub s. These are impedances, and we can also, by definition, note that the product lambda rho is equal to the compressional wave impedance squared minus 2 times the shear wave impedance squared, and that the product mu-rho is equal to the shear wave impedance squared. So the challenge for us at this point is really twofold. We need to determine the R theta of t's, or the RT t and thetas, and then once we determine what the R's are, we should be able to determine what the impedances are, because as we've talked previously, we know what the relationships of impedances are to the reflectivity. Now again, I'm just kind of coming back to this relationship here. We're doing this because the lower lambda-rho mu-rho region tends to give us a pretty good insights into the location of the high TOC regions, and so we'd be using seismic data, of course, in order to do this, but again, that's our motivation. Now, as we talked about, our AVO observations provide these R sub pp of theta and t, or R sub p of theta and t sub I. And so we have, at a particular time t sub I, we can take the amplitude variations that we see as a function of theta, and we know what these coefficients are. We can calculate these coefficients. And we can then, the problem then is to determine, once we go through this process of calculating A, B, and C, the coefficients, our task is to determine what the compressional wave, reflection coefficient, shear wave, and density reflection coefficients are from an inversion of the observation. So we have all these observations at these different times, t sub I, and t sub I could run from whatever time of interest you are, in your zone of interest, to from some minimum to some maximum, and then you're looking at probably a common range of offset angles. And so these are observations, these are knowns, and our problem then is to determine what these R sub AI of t sub I are, R sub SI, R sub D, for each time. Once we do that, as we've noted, once we figure out what the reflection coefficients are, what the reflectivity is, we should be able to determine what the impedances are. And once we've determined the impedances, then we should be able to, we talked about this recursive estimation of the compression wave impedance, or the shear wave impedance, is this product of terms, 1 plus R sub I over 1 minus R sub I. And we should be able to work from that, determining what the A sub I's are through this recursive inversion process, back to the product, lambda-rho, and mu-rho. So we're at this point now. We've talked about the inversion of this data using the Marquardt-Levenberg approach. We should be able to take our amplitude variation with offset observations, convert those into these compression wave, shear wave, and density reflection coefficients, and given the reflectivity, we should be able to work recursively back to the impedances referred to in Russell 2014, for example, as compression wave impedance AI, shear wave impedance SI. And so that's our task, and that concludes the overview of the topics that we've been covering in the last 13 or so videos. And this formulation, is one of the outgrowths of the AVO analysis that we've been talking about in Russell's paper. We get that lambda-rho, using that notation, we could express it as A sub I squared minus 2S sub I squared, mu-rho equal to S sub I squared, or we could, using different notation, again, just to make sure that we're seeing the same thing here. We're just using a different notation for the acoustic impedance. So lambda-rho could also be expressed as Z sub P squared minus 2Z sub S squared, and mu-rho as Z sub S squared. So these are all equivalent. And in the next video, we're going to elaborate on some approximations to the recursive inversion approach using a Taylor series expansion approximation of impedance. And again, hope this has been helpful. Thanks for joining us, and we'll see you next time.